Hi, I'm Andrei Popovich. Welcome to episode 2 of the Typechecker podcast. Today, we're going to be talking about a functional programming language called Granule.
So my name is Dominic Orchard, Dr. Dominic Orchard. I'm a lecturer at the University of Kent in the School of Computing here in the Programming Languages and Systems group. And generally, I work on extending the power of programming languages to make them more expressive, but also to introduce more reasoning and verification into the programming languages. So this project I've been doing is the Granule project, which is sort of a particular thrust of my work in that area to do with types.
So tell me more about Granule.
Granule it's an experimental functional programming language. It looks a little bit like Haskell or OCaml or Agda or something on the surface. And we're sort of exploring via Granule how to express properties of how data is used inside of the type system. So we're using the type system as a way of capturing more properties of programs. And we're doing this by combining two ideas. One is quite an old idea. It's the notion of linear types, which has been around in the research literature for a little while. And then the other is the concept of graded modal types, which is much more new. And it's an area I've been working in for a little while. So we're kind of bringing those two things together and experimenting with them in the context of a fully fledged language and with lots of different sort of modern programming features in it.
So, okay, let's try and unpack those. As I understand, a linear type is basically a way to say that a value must be used exactly once.
Yes, so this is the basic idea of linearity. You have a value and it must be used. You can't duplicate it, you can't throw it away. This linearity restriction sounds really intense, right? It sounds like, oh, you basically couldn't do anything. But it's a really useful basic notion of treating data as a resource, as something which gets consumed, that gets used up. And on top of this, we then build the ability to actually use values more than once, use data more than once, but understand in which way it is used. So we think of the linearity as like our base layer that gives us this very strict and strong view of things. And actually, in the original work on linear logic and linear types, going back to sort of 1980s and 1990s, the idea is that you split data into two camps. There's the data that's linear, which gets used, gets consumed exactly once. And then there's data which is just unconstrained, which you can do anything with, which is sort of how most programming languages treat things now. So it kind of splits things into two camps. And our idea in grading is to, rather than just having two camps, is to have a whole spectrum that goes from linear, used exactly once, and this whole spectrum going through where we can understand exactly how data is used, how many times it's used, where it's used, what's done to that data, where does it go, and so on, right through to at the other end of the spectrum, completely unrestricted. We don't care what's done with it.
Would it be possible to say that some data isn't used at all? I know this is common in some proof systems where you want to make sure that a piece of data exists, but you don't need to use it.
That's right, yeah. So you can say this thing is thrown away. It's not used in this context. Yeah.
So one example where a linear type might be useful is with file handles. A file handle is kind of an unusual situation where you get one once you start reading a file, and then eventually you're supposed to close the file and stop using the file handle. The reason this works well with linear types is because we say you get the file handle and we say it has a linear type, so you have to use it exactly once. And then the only way to use it is to close the file. The compiler will guarantee that anything with a linear type is used exactly once. So every file handle that gets opened has to be closed and then it can't be used anymore.
Yeah, so this is a well-known sort of long-running example in this kind of community. And it's quite nice, it's quite cute. You're recognizing the fact that a handle is a piece of data which acts as a proxy for some external kind of physical resource, in this sense, a file. And when we use it, we want to obey a kind of stateful protocol, which means that we want to apply operations in a certain order. And we have an operation which creates it, and we have an operation that destroys it. But we don't want to ourselves just discard it in the meantime. So the combination of the linearity and the way the programming interface is defined means that whenever we open a file, we always close it. And once we've closed it, we don't do anything else with it. And this generalizes not just from files, but to also other kinds of stateful protocol. You can use this as a way of embedding communication protocols and other kinds of protocols where you have a piece of data that acts as a proxy for something else, like maybe a sensor or a robot arm or something like this, where you have a sort of sequence of steps, and you want to make sure that things are shut down in a particular way or created in a particular way. And these handles remain abstract, so you can't actually inspect them yourself. You have to use the programming interface. So we put this example in our paper just to kind of remind everyone that linearity on its own is really useful for doing things like this. Okay, this is just one kind of particular example of a particular kind of program. There's lots of times when we need to break out of that linearity, and that's where the modalities come into play.
So there's actually a little hole in my explanation from earlier. I said that you get a file handle when you open a file, and then you destroy the file handle when you close the file. So my question is, would it be possible to have a function that takes a file handle and reads or writes with it, but somehow using that function doesn't count as consuming the file handle? Like, can we say that just because you've used this function doesn't mean you've used the file handle?
Well, only if that function indeed did not actually use it. So in terms of the soundness of the system, we could build something like that if that function didn't use that handle. Now, in the case of primitives like reading a character from a file or writing a character to a file, we know that we do actually have to use that handle. We are actually inspecting it and doing something with it. That might be built in using some primitives. In Granule, there's a sort of built-in primitive for that. So it would be unsound to mark that as something which doesn't actually get used. So we do end up with this kind of slightly perhaps clunky programming pattern where every operation that uses a handle, it takes a handle and returns it back. That's a kind of feature of the design here, which is perhaps a little bit annoying, but also it's a good way of then enforcing that you actually obey the protocol correctly. So at the end of the day, it's kind of a design choice, but that puts you in the space where you can actually do verification that you have adhered to the protocol.
And then for cases where linearity is too restrictive, like if you want to log a value and then return it, you can grade it so you can use it multiple times?
Absolutely, yeah. That's one thing that they can give you.
So I think we've mentioned graded modalities or graded modal types before a couple of times. I was wondering if you could go into some more detail on that.
Yeah, absolutely. So the idea of modal types has kind of been around for a long time. It comes from modal logic. And in logic, the idea with adding a modality is like a way of capturing some additional reasoning about some sort of abstract outside world that isn't already represented in the logic. So it's used for talking about the worlds in which something is true, the possible worlds in which something is true, or some additional information that, like the origin of some information. So it's a kind of way of extending the expressivity of a logic. And in programming, we've been doing something quite similar for a while with various kinds of modal types, which capture some additional properties of our program. So a sort of very well-known example, which is popular in Haskell, is monads. They are essentially a programming interface which you can use to capture various kind of side effects, for example. And from the perspective of the type system, you've got this type which represents the type of effectful computations producing a value. And we can describe this as a modality. It's saying, here's a program and it does some additional stuff out in the world, like it does some state or some IO or exceptions, and then it produces this value. So these sort of modal types are quite nice, a way of capturing additional properties of programs, but they're very binary. So say when we're writing Haskell, if we're not using monadic type, then things are sort of pure with regards things like state. And then if we use our state monad, we've got this state data type, we know, okay, this thing can potentially have stateful side effects. The idea with graded modal types is to make this distinction more fine-grained. And rather than just having a single type constructor, like the state monad that captures the fact that this thing might have state, instead we have this whole family of type constructors which are indexed or essentially annotated with a little bit of information that tells us more about what's going on inside. So rather than just having a state monad, you can have a graded one which tells you, oh, well, this computation, it does some reading and it does some writing. Or this computation here only does reading. So that affects what you might want to be able to do with it and what you're allowed to do with it. So the thing that only does reading, you could then do that in parallel with something else that only does reading, and you wouldn't get any problems. So the idea with grading is to capture more properties of a program, more fine-grained properties at the type level by these grades. They're sort of annotations that come along with the types. And there's a kind of slogan that we like to use often about what's going on with these grading modalities, and that's that we want to have structure in these indices, in the indexes of the type constructors, when we want to have structure there that mirrors the structure of some semantics or of some typing rules or some proof theory, as a way of then capturing properties of it in the type level. And if that's a sort of long description, and maybe a short one is, it's a way of getting more information into your types.
Something I find super interesting about Granule is that under the hood it actually uses an SMT solver for type checking. I wondered if you want to talk about that.
So with the graded modalities, we make them quite expressive. So you can write some quite general functions which then generate some quite complicated constraints. And one thing that makes this even more complicated but also more interesting is that in Granule we also have index types, which are kind of a lightweight form of dependent types.
And for the listener, index types are like GADTs in Haskell. Now back to the show.
So I can take in parameters which have type indices, which then can be used in the grading expressions. So for example, you can talk about, I have this list of length n, and then I have this function which I have the capability to use exactly n times, and then I'm going to apply that to every element in the list and get a list of length n out. So there's a connection there between then indices of inputs and the grades. So you can write quite complex first-order logic expressions which quantify over natural numbers and do multiplications with them, and then you can do this for different grades as well, not just for natural numbers. We have things like lattices. So there's quite a lot that you can do in the grades, and I just thought, I don't want to write my own solver for this. There are people who've done a lot of really nice work already writing really nice solvers for things like this. So we use the Z3 SMT solver produced by Microsoft, which is a really nice open source SMT solver and is really optimized and very fast. It was basically a case of, well, why do a lot of work rolling your own solver when you can use someone else's much better engineered system?
Do you think it'll be possible for the programmer to define their own graded types in the future, or will it be restricted to just the ones that are built in?
Yeah, absolutely. That's where we're heading. So at the moment, in the current sort of implementation, there's just a bunch of stuff built in. And if you want to add your own, you have to start editing the compiler, which is actually not that hard. But of course, we don't really want people to do that. So what we're working on is being able to have sort of user-defined graded modalities. That's not too difficult in some places, but the difficult thing becomes, one, how do you know that this thing actually obeys the right properties for your particular style of graded monad? And two, how do you then do the type checking? If someone's built their own kind of custom notion of grading, how do you then discharge those constraints? So that's a slightly tricky sort of engineering problem. Do we want to expose the interface to the SMT solver, or actually we have an internal kind of symbolic machine first before the SMT solver? So there's questions about like the best way to allow people to have that user extensibility. But that's what we really want. It'd be really nice to, you pull in this library and it has some nice built-in graded monad for doing a particular thing, or graded comonad for capturing a particular property. That's where we'd like to go with this work, yeah.
So Rust has their own system for managing resources, sort of similar to linear types called the uniqueness types. I was wondering if Rust's system could be implemented in Granule, maybe even as a user library, rather than being built into the compiler.
Yeah, I believe so. So I think Rust has some of the similar philosophies that are embedded in Granule, this idea that not all data is free and unconstrained. Like some data you want to treat carefully, so they have their borrowing notion for pointers and so on. My hope is that we could encode this kind of thing. It seems like having linearity as the base and then being able to kind of build data flow properties on top, that should be doable. We haven't tried it. I'm not a Rust aficionado, but yeah, it's on the big stack of, this would be really cool to try and we'd love to try it. There's definitely some thematic crossover between Rust and linear types and Granule work. And I think with the grading, that gives you a lot of expressivity. It's not just linear types, it's the grading that really is the power here.
Another thing that I thought would be interesting would be staging. So often you want to say, like, I need to know this parameter at compile time. It can't be a runtime thing. Do you think that Granule's grading or comonads could kind of help with that?
Yeah, absolutely. So there's a really lovely paper from almost 20 years ago now by Rowan Davies and Frank Fenning called, it's something like a modal analysis of stage computation. And they have an S4 necessity style type system which captures compile time versus runtime values, and the compile time is captured by their modality. And our system is very similar to that. It's a sort of a graded generalization of their system almost. Okay, we have lots of other stuff going on, but there's a common core there. And it's something that my PhD student, Willem Leopelt, has already started experimenting with. And we did have a sort of prototype that was basically their work, but using our modality, our comonadic modalities. And we think we can do it like a nice generalization of that to multi-stage programming, not just compile and runtime, but use the grade to tell you at what stage something lives, and then you can have a whole like pipeline of stages, and compile time, runtime, and JIT, or this language and this language and this language and this language, and so on. So again, this is on the great big list of work that follows, but we're much more confident about this one because there's already stuff in the literature that really is quite close theoretically to the structure of our system. That's definitely something that's on the horizon.
That sounds pretty exciting. I was wondering if you wanted to talk about how you even got started working on Granule.
So that's a really interesting question. I think it's something that's often like hidden in research, like why do people do what they're doing? So in some ways, this work started way back in my PhD, probably about seven years ago now, back in 2012. So I was working with Thomas Petricek and Alan Mycroft, and we kind of presented this idea of what we call co-effects. This was about having a type system that tracks how you use the context in your program. And we built a kind of general system that you could parameterize with different algebras to capture different kinds of property in the type system. And this is something that other people were also thinking about they were coming at it from a point of view of linear logic and generalizing some of the work that had been done in linear logic and bounded linear logic. So there's sort of a bubble of activity in this area in co-effects in sort of 2013, 2014 that I was involved in. And I kept doing things in that work, and then we looked at the effects side of things and structuring computations using graded comonads and graded monads and kind of getting these properties in the types. And as I went on, I was giving research talks and saying, it would be really cool if we could build a language out of these things, and it would give you a way of doing this additional reasoning and getting additional verification. And I sort of said that a few times, and then it was in 2017 I was scheduled to give a talk in Edinburgh about co-effects and effects, and I'd started kind of using this terminology of graded modalities to describe both of them together as a more like a unifying framework. And then I thought, you know what, I'm okay at programming. I keep saying that we should build a language out of this thing. Why don't I just try and build a quick little prototype language that I can demo in the talk? This was sort of a couple of weeks before the talk. So I sat down, kind of not having huge expectations, but sort of bashed something out and sort of started playing with SMT solving as well. And it sort of came to life in my hands. I thought, oh, this is really cool. And then once I had it in my hands, I started thinking about all these problems and all these kind of interesting things we could do with it, which I never thought of before by just sort of staring at the theory. So how do we deal with polymorphism in the grades, and how do we deal with polymorphism in the graded modalities themselves, and what does it mean to then have index types, and what does it mean to have pattern matching over things which are graded modal, and how does this work with the co-effects? And it just sort of snowballed from there. Like the more I played with it, the more interesting it became. So it was nice to see the theory come to life, and then for it to kind of take on a life of its own and generate really interesting examples and generate its own questions. So it was definitely a case of sometimes implementing your theory is a really nice way of moving along the research. And I'm really glad I did it. And I was able to pull in other interested people like my PhD student Willem and Harley. And so we're sort of working on the theory and the practice at the same time now, and doing things in the theory and looking at them in Granule and vice versa. So it's been a nice activity to bring the two together.
Thanks, that's really interesting. In case any of our listeners are interested in learning more, where can they find more information about Granule?
If you just Google for the Granule project, you can find our webpage, granule-project.github.io. From there, you can download Granule from GitHub. We've got some releases, some binary releases recently. There's tons of examples. There's also like a starting guide. So, we're always happy to have people ask us questions, send us emails, add tickets on the GitHub, or fork it and do pull requests. We'd love that. Or if you're someone who's doing research or wanting to get into research and you're interested in PhD positions or postdoc positions, then you should definitely get in contact with me. I also have a collaborator in the US, Harley Eads at Augusta University. He's working on this project with me, and he also has potential for taking people on as well on this project. So we're always happy to have interactions with people.
Great. Thank you so much for coming on. Everyone, please check out their website. It's really cool. They're working on a dependent type implementation, so that's even more powerful than GADTs. They have a lot of really cool stuff going on, presentations, papers. I'm really excited to see where it all goes, and thanks again for coming on.
No worries. Thanks so much for asking me to do this and for your interest in the project.
All right, and thanks for listening. I think that's a wrap.